Now let's get to the point. Different molecules will have different electron distributions. This is what I mean. Let's look at water. Specifically, let's look at the top half of water, the oxygen. This oxygen is an extremely strong, meaning electronegative atom. So it's going to pull very hard on the electrons it's sharing with the hydrogen in these bonds right here. In this bond and this bond, those are actually electrons. The electrons are going to be more towards the oxygen, so I guess it's going to be bigger up here, and less towards the hydrogen, so less down there. It's shared, but they're more towards the oxygen. In addition to that, it has these 4 unpaired electrons that it's not sharing with hydrogen at all. So the top half of this water molecule is full of electrons, so this is extremely negative. It has the 4 unpaired electrons that it's not sharing, and it also has the bonded electrons that are closer to the oxygen than the hydrogens because of the electronegativities. The bottom half has 2 hydrogens, and these are really weak. They don't pull electrons hardly at all. So these hydrogens are sharing electrons with the oxygen, sort of like the way that you shared your Game Boy with your big brother. They had it most of the time. So the top half is going to have most of the electrons, and the bottom half has almost none. It has only the nuclei of these hydrogens, which are positive, full of protons. So the top half is going to act electrically negative, and the bottom half is going to act electrically positive, even if overall this whole thing is neutral, because the negatives are on the top and the positives are on the bottom. So this water molecule really looks kind of like this. It's split into a positive top half, a positive bottom half, positive hydrogens, and the negative top half, negative oxygens. If you looked at it in 3 dimensions, it would look kind of like this. Now these dots right here, they're invisible. You can't see them. They're hanging out around here, but they're electrons, not atoms. So in 3 dimensions, you see you have the positive charge up here, and the negative charges down here. And I'm sorry about this, but this particular slide uses negative as red and positive as blue. That's the opposite as on my other ones. This is the only picture I could find about a 3D water molecule's charge density. Okay, so in contrast, let's look at carbon dioxide. Its electrons are sort of symmetrically distributed, and what I mean by that is it's true that the oxygens are electronegative. They're holding most of the electrons, and the carbons aren't. So the carbon is a little bit positive, and the electrons are a little bit negative. But these oxygens are pulling equally in opposite... Oops, that shouldn't happen. Let's see. But these oxygens are pulling equally in opposite directions. So it's not like the electrons are sliding to the left or to the right. They're staying where they are. So it's like a tug of war where both teams are equally strong and the electrons aren't preferring either side of the molecule. So no side is particularly positive or negative. They're both neutral. We have 2 different categories of molecules. The ones that have directional electron distributions, like water, where one side is negative and the other side's a positive. And then we have ones that have no electronic direction, basically. There's no part of it, there's no half of it that's positive and half of it's negative. Okay, so the following 2 vocabulary terms, it's the whole point of the lesson. All that stuff before was just so that you could understand this. Chemicals with non-symmetric charges, that is, chemicals where one part of it is positive and one part of it is negative, these are called polar. It's called polar because it acts like a magnet with a north pole and a south pole. Except it doesn't have a north and a south pole. It has a positive pole and a negative pole, but they act really similar. Chemicals that have symmetric charges, so they don't have a positive and negative end, maybe they have positive and negative parts, but that doesn't matter because they're in a tug of war and they're totally tied, so they end up being neutral. These are called nonpolar. They're the same from every side. They have no sort of magnetic or electric poles, and they don't respond to electric or magnetic fields at all. Polar molecules and nonpolar molecules, they act and they interact differently. They're going to be important in this unit. It's an important distinction, and knowing whether something is polar or nonpolar lets you describe a lot about its behavior and properties. So let's summarize. Different chemicals are going to have different electron distributions. If these electrons are distributed symmetrically, and that means like in a tug of war where they're tied in every direction, it's going to be called nonpolar. It's not going to respond to electric fields or forces, and the electrons are going to be more or less evenly distributed. But if they're not symmetrically distributed, for example, one side has a lot and one side doesn't have a lot of electrons, it's going to be called polar because it has a positive pole and the negative pole. And it'll act like a little tiny molecular magnet. If you know the word nonpolar, polar, and what this actually means, then you will have learned what you're supposed to from this lesson. I hope this was helpful.